So many thanks to the three breakout session leads, and thanks for the summary and managing the breakout sessions. So we're ready now for the last talk of the day. I'm very happy to have Mark, even if it's remote. We're very happy to have him present here at QSig because Mark Zhandry, a senior researcher at NTT Labs and formerly, as I understand, at Princeton University as assistant professor. So Mark has done an impressive amount of significant advances in this area of quantum systems, and a lot of the results we've been discussing today, including one-shot signatures, are works that he was part of and breakthroughs that he put forward. So I hope we have Mark on the other side of the line. Okay, all right. So Mark, are you able to hear us?
Yes, I can hear you.
Maybe we can also hear him. Hopefully.
Are you able to hear me?
Yeah.
All right.
Okay, just checking the sound. Are we good? Yeah, so Mark is good. Are you able to hear us?
Yes, I can hear you.
Fantastic. So I think we're ready, and you're good to go.
All right, great. Yeah, so thank you for the introduction, and I'm very happy to be here today. Got the time zones worked out so I could show up. Yeah, so I'm going to talk about the status of quantum money and variance that includes one-shot signatures. And for the purposes of this overview, I'm going to assume we have fault-tolerant quantum computation. Of course, we don't, but I'm just going to assume it. So the three things I'm going to be talking about today are, so on the right, we have one-shot signatures, the focus of this workshop. But one-shot signatures are rather strong objects. So I'm going to talk about also two objects that are implied by one-shot signatures. So in the middle, we have quantum lightning. And then on the left, we have the weakest object. I'll be talking about quantum money. And the reason I'm talking about these is they're all, in my view, kind of open questions, how to construct these in convincing ways. So we have a few different paradigms for constructing quantum money and these related objects. I'm just going to kind of go through them, explain what I think the, how good they are, I guess, and whether or not I think that they will be useful for realizing one-shot signatures. So the first I want to talk about is the hidden subspaces paradigm of Aronson and Cristiano. The advantage of this approach is that we actually can securely instantiate this from indistinguishability obfuscation. So we have actually like a pretty good understanding of at least one way to realize this and prove it in a secure way. The downsides are that it's impractical. IO is this really great tool, but as it stands, is currently impractical on a classical device. So certainly it would be on a quantum device as well. And right now, this is really the only obfuscation. General purpose obfuscation is really the only way we know how to instantiate this paradigm. So it's a nice open question if we can instantiate this paradigm with some weaker tools, and actually this starts pushing up on some known barriers in just classical cryptography from, say, learning with errors or other cryptographic tools, where we're often stuck at obfuscating programs that are evasive, meaning that it's hard to find an input that the program outputs 1 on. And for quantum money, it seems like we really need the non-evasive obfuscation. So there's kind of this big barrier there, and an interesting open question. Then the other, not amazing thing about the hidden subspaces approach is that it doesn't seem amenable to quantum lightning or one-shot signatures. And the reason is that for both quantum lightning and one-shot signatures, you need some security against the mint itself. You can kind of think of these stronger variances having security against the mint. But in the case of hidden subspaces, if you know the subspace, which the mint would need to in order to actually mint the banknote, then you can actually just mint as many as you want. So there's really no security against the mint here. Another framework that was first introduced as a special case by Farhi et al., and then we kind of abstracted it in a work last year, is something called walkable invariance. And here you have some invariant or function that takes as input a large domain and hashes it down to some small invariant. And additionally, you have this ability to kind of walk around the subspaces of any output. The subspaces of any set of inputs that all map to the same output. And what's nice about this is there is some sort of security justification. It's not as good as a proof relative to a widely studied cryptographic assumption, even one as potentially sketchy as obfuscation. But we can prove it under something called a knowledge assumption, plus sort of some statistical assumption about how the invariant works. Unfortunately, I'm personally a little concerned about this knowledge assumption. It does. In a very recent paper, I gave an attack on a version of this knowledge assumption in another context that I'll get to in a couple of slides. It doesn't break necessarily the assumption on any particular invariant, and it actually doesn't indicate any attack on the scheme, but it sort of shows that the security analysis is maybe questionable, and this structure just seems hard to analyze under nice assumptions, so I'm not really sure what to make of the security. I think it's open. In terms of if it's going to be practical or not, unclear. I don't know enough about not. So the Farhi et al. Paper used some hard problems on knot diagrams. I'm not really familiar with how big you need to set your instance sizes to be secure. And they give an instantiation over isogenies, but it's an incomplete protocol, so we can't actually implement it, even if it were efficient. What's nice about this is that it does readily give quantum lightning. There's this collision resistance property of the invariant, and if that holds, then you get quantum lightning almost for free. So that's pretty nice. Sorry, it's not collision resistance in the classical sense, but it's still hard to find superpositions of all inputs that map to a particular output. And it's hard for anyone to find these given the output, and this is what kind of makes it readily give quantum lightning. But it's actually not collision resistant because we do have the ability to walk around the pre-image sets. And because it's not collision resistant, it doesn't seem amenable to one-shot signatures. Now there's this other approach called commuting unitaries that was introduced by Kane et al. And they instantiate the commuting unitaries framework with quaternion algebras. I think it's an interesting approach, but it needs a lot more study. The particular instantiation is kind of hard to get at if you're not an expert in the area, and so I just think it needs a lot more study. And like all the previous ones, it doesn't seem amenable to one-shot signatures. Here, the reason is there's really no classical structure. The money states are kind of essentially random states. And so there's no classical structure to actually try to find a classical signature through this. So a nice open question here is if we can find other instantiations of this framework that might lead to things we can prove secure or make practical. A new framework that I introduced, it'll be appearing in ITCS next week actually, is using something called a cryptographic group action. I won't really describe what these are due to lack of time. What's cool here is we can prove security under reasonable assumptions. Plus, we need a black box model for isogenies, but I think this would be pretty well accepted by cryptographers. So I think there's a good security justification. I also think it's relatively practical, assuming we had fault tolerant computation. Limitations are that isogenies are the only way we know how to instantiate these abelian group actions right now. So there's an open question of if we can get other instantiations. And also for kind of the same reasons as the invariant framework, this doesn't seem amenable to one-shot signatures because basically your states are a uniform superposition over kind of an entire domain, and the sort of the classical information, which in money would be the serial number, is in the phase. And having things in the phase, it's not clear how you find like a classical string that can be verified against your public key in the case of one-shot signatures. So while it does give this quantum lightning object, it doesn't seem amenable to one-shot signatures. And then finally, the only currently published instantiation of one-shot signatures. I don't have a name for the framework. I on the slide it's called a fractured subspaces. Basically, we decompose the domain into a bunch of linear subspaces, and then create an oracle that maps each of those subspaces to a unique string. And the reason we use subspaces is that it allows for the kinds of verification procedures like the Ernst-Cristiano subspace oracle. The problem is we have a really poor understanding of the security of this. It's also impractical because the only way we would know how to instantiate it is with obfuscation. But we can at least, at least if the function we provide is collision resistant, it does give us the one-shot signatures. And so the open question here is, can we justify the security of either this candidate or any other candidate for one-shot signatures? And then I'll just conclude with kind of a speculative direction, which is that Unruh in 2016 gave a quantum oracle. His purpose was completely different. It was kind of exploring the post-quantum security of hash functions. But relative to this oracle, now we know that one-shot signatures exist. And the question is, can we obfuscate this oracle? Now, the problem is that Unruh's oracle is quantum, not a classical oracle. So there's no hope of heuristically using classical obfuscation techniques. You really need to be able to obfuscate quantum programs. And here, this is actually just a generally a fascinating question of how can we obfuscate quantum programs. There's been a line of interesting works. There's a typo here that should be the last work there should be 2024, not 2014. But right now the existing quantum obfuscation schemes only work for, yes, quantum programs, but the programs have to have classical input and output behavior, and this is really not what Unruh's oracle does. So the question is, can we try to obfuscate Unruh's oracle in some way, either by extending these techniques or something else? And really that's all I wanted to say about kind of the different paradigms for trying to construct quantum money and these variants. So I'll just end here.
Right. Thank you, Mark. And I should say this is exactly how we planned it. We wanted to have a good amount of time for Q&A. We're also like at the end of the day here. And we already had the opportunity to discuss a lot of these issues. But Mark, thank you so much for giving like this this broad overview exactly of what was in the minds of many of the participants here. Exactly what are the options? Like that's a great way to have this as a summary at the end. And now I'm going to open the floor for Q&A from the audience. All right, please go ahead.
Thank you very much. Yes, thank you for the great talk. It was quite an informative overview. I have a question specifically about you called it fracture subspaces, but I guess affine partition functions.
Sure.
You say that the implementation that you have uses obfuscation, that the obfuscation is impractical. Would you be able to briefly comment on what implementation you have and what kind of obfuscation you apply to it?
Good. I mean, it's all just heuristic. So we described this oracle in the paper. The oracle we describe in the paper is not an efficient programming. So it's like applying random functions and stuff like that. I don't think we mentioned in the paper, but we can kind of turn it into a the function into something that's actually efficient using pseudo-random functions. It's slightly non-trivial, but this is something that we can do. And so what I'm imagining is just creating an efficient version of our oracle using pseudo-random functions, and then obfuscating that oracle using general purpose obfuscation. Now we can't prove anything. If assuming indistinguishability obfuscation or really any form of obfuscation that cryptographers have studied, we right now can't actually prove anything about whether this scheme would be secure, but it at least gives a heuristic instantiation of this approach that could be a one-shot signature. The problem though is that I don't see any way to avoid the use of general purpose obfuscation with our approach. And general purpose obfuscation, as I said, is quite impractical right now.
Okay, thank you very much.
Thank you, Mark. Actually, the follow-up question is here only obfuscation itself impractical, or well, how about these oracles? Do they have like a compact? Can they be instantiated by something which is compact, not so big? And if we apply some heuristic obfuscation?
Yeah, I mean, it's certainly possible, but again, it really seems like you need sort of the function is complicated enough. It has these subspaces. It's going to have pseudorandom functions that it really seems like you need some mechanism. Right? So you have this function, trying to turn it into basically a black box. And if you're going to use obfuscation, it really seems like you need general purpose obfuscation. The kinds of obfuscation that are actually practical, things that have existed for decades that just perform sort of basic code operations, don't really seem, the consensus is in the community is kind of those don't really seem like they're secure in terms of actually hiding cryptographic secrets, like PRF keys and whatnot. And so it really seems like if even though it's heuristic, it seems like the only chance we have of going via software obfuscation to get this to work is to use the inefficient general purpose indistinguishability obfuscation kind of techniques. You could potentially get something in a hardware model, a trusted hardware model that is that would be reasonably practical, but yeah, in a software model, then it really seems like we're stuck here. At least that's my take.
Thank you for the very nice talk. So I was very curious about two of the approaches you mentioned. So one based on the walkable invariance, and the other one based on the abelian group actions. So if I understand correctly, both of them rely on some assumption, but which one do you think is more promising, or to maybe weaken that assumption and yeah, make it closer to the final goal?
Good. So yeah, they're kind of incomparable, I would say. So as I said, the walkable invariance, what we can prove is we need a knowledge assumption. And knowledge assumptions, even in the classical world, are met with suspicion. And I think in the quantum setting it's even worse. And the reason is, so I go into this in this recent paper on group actions, but it turns out that there's kind of a natural knowledge assumption way to prove this group action thing as well, but that knowledge assumption is actually false. There's an attack, and so that kind of challenges the intuition of these knowledge assumptions. So what does the knowledge assumption roughly say? In the walkable invariance setting, it says that if you can find 2 points with the same invariant, that you actually must know a path between them. And in the group action setting, it's kind of similar. It's like if you can produce 2 points in the group action, then you must know the group element that actually mapped you from one set element to the other. And what I show in that paper is you can actually create two group elements without, in some formal sense, without any knowledge of how you got there. So the knowledge assumptions I find to be rather questionable in the quantum setting, because you can do things like, I don't know, you measure in the Fourier basis or something to destroy information. There's just it's hard. It seems very hard to pin down a knowledge assumption that is convincing. And what's also interesting is that in the quantum setting, an oracle, like a random oracle or whatever oracle, a black box model usually allows you to justify knowledge assumptions. And in the quantum setting, this turns out to not be the case, and it's for an interesting reason. So the way in a black box model that you justify knowledge assumption is you kind of look at all the queries you made to the black box model, and you show that reveals whatever knowledge you're looking for. But in the quantum setting, you can't look at the queries, because looking at the queries actually messes them up and will potentially cause the adversary to fail. And so for that reason, in my recent paper, I make some arguments that actually a black box model is potentially more reasonable than a knowledge assumption in the quantum setting, which is kind of backwards from what we expect in a classical setting. And for this reason, I tend to prefer this group action one, because there is a reasonable assumption. It's still not quite a standard assumption, but there's a reasonable assumption on the group actions plus this black box model that we can use to justify security. So I like it for that reason. I guess in terms of if the goal is one-shot signatures, I think, as I said, I think both are not really amenable to one-shot signatures, but the abelian group action just feels a lot less amenable, because there's really like the information that is really stored in the phase, and it just seems hard to turn that into a classical string. Whereas, who knows, maybe with invariance, there's, even though it's not collision resistant, maybe there's some way to kind of like still find a signature in there, because it's, this classical function, and you're classically walking around the invariant. But that's just sort of big intuition. But anyway, I think they're really incomparable. But as of today, I kind of prefer the group action approach, just because of the potentially cleaner and more reasonable security arguments.
Thank you.
Nick Spooner was talking about non-collapsing hash functions, and the existence or non-existence being a big open problem. Mm-hmm. Does your intuition lean in one way or the other regarding this question?
No. So I mean, I think, is it actually formally proved that non-collapsing collision-resistant hash functions imply one-shot signatures? But they're very close, these objects, and so you could there is a distinction between them, but for the most part, in this whole discussion, you could replace one-shot signatures with collision-resistant but not collapsing hash functions, and kind of the same thought process applies.
Yeah, and I should just add that Nick's presentation was exactly making that point. So exactly, okay. Regarding non-collapsing plus collision resistant. And do we have more questions from the audience? Mark, I should say, perhaps the question aligns with also what the slide you have here, but I want to just highlight this aspect a bit more, because this also goes back to the quantum lightning paper, so that there is a lot of tension between non-collapsing and collision resistant. So it sounds like from our conversation and also comments we had before that it might be quite promising here to somewhat relax, on collision resistance, try to get something weaker there, and then see what of the applications of one-shot signatures are still like, you know, feasible, or we might able to get quite a few interesting things by somewhat, you know, being more relaxed about collision resistance, but being able to control somehow the type of collisions, and making sure that the design still, you know, is amenable to the particular use case or application that we want to get. So I was wondering whether you have any further comments on that direction.
Yeah, so, I mean, certainly that's something that could be the case. So, for example, quantum lightning gives you a protocol for certifying randomness. Now, the certified randomness is somewhat weaker than what you get from one-shot signatures, because in the quantum lightning case, the proof of entropy is actually a quantum state, not a classical state. But it does show that, like with quantum lightning or these weaker objects, there is hope to get you know, some subset of the applications. I guess the problem though is as long as you want classical communication in your protocol, you know, it seems like quantum lightning is not going to be quite enough, because quantum lightning really seems like you're always going to need a quantum state. So you need to somehow figure out a primitive that at least some of the algorithms are classical, if you want any hope of something with classical communication. And you know, certainly this is something that could exist, and you know, like this walkable invariance might be a nice place to look, because you know, a lot of the walkable invariant framework is classical function, classical walks around the preimage sets. But yeah, as of now, I don't really have any like concrete ideas on what this primitive would look like.
Right. Thanks. Do you have any other questions for Mark? All right. So I think we're now wrapping up with the end of a long but hopefully very interesting day. So let's give a round of applause for Mark again. Thank you very much for the.
Thank you.
All right, and I think just